Okay, Assalamualaikum warahmatullahi wabarakatuh and good morning. Okay, can somebody respond to me whether you can hear me or not?
Good morning, Doctor.
Okay, good morning. Okay, 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 can you see the screen is full or not?
Yes, Doctor. I can see the full.
Okay, good. So today we continue with a new ideal transformer. Okay, last week we already learned about the theory of transformer. Okay, for today we continue on a ideal transformer, which is mostly on calculation. Okay. So what is ideal transformer? Okay, so basically an ideal transformer has no winding resistance and has no leakage inductance and iron losses. So what is that mean is that, okay, I think this one is much more better. Okay. Okay. So what it means that for a transformer or anything is actually ideal and practical. Okay, and ideal one and practical one. Ideal one we usually use for calculation, easy calculation, and for practical one we want to know the real quality of the device. So for ideal one, you just have something like this. Okay, so you have a winding here. Okay, and you have this. Okay, for practical one, you have a, if you can see here, you have a winding resistance. So you have winding resistance, something like this. Resistance. Okay. Okay, and okay, you have a winding resistance, a leakage inductance. So basically, leakage inductance is something like this. So if you recall back, there is a leakage when you do winding. There is a leakage flux. So it will represent as inductor. And iron losses is something like this. Okay, it's represent as resistance and inductance. Okay. So basically you have ideal and practice. So for today we focus on this one. So you have to master this one before you can master practical one. So magnetized current, flux, generate induced voltage for both windings. So basically V in, okay, what it means that if you have a voltage source here V1, okay, and this is the output V2, okay. So basically all the voltage here will be induced here. This one is E1, okay. This one is E2, okay. So basically all the voltage will be converted. For this one, it is this one is V1 is not equals to E1, okay. So that is the difference because practically there will be losses. But in ideal condition, the voltage here is same as induced electromotive force. Remember that E, okay, V and E. So make sure you know voltage of V is outside, E is inside. Okay, so make sure you know the difference. Okay, and another thing you need to know is what is the generated flux. So the formula is this. So E is equals to N1 flux W over square root 2. So this one is not a popular equation, but this one is. Okay. So if I look give here. So usually if they ask if they give flux or they ask what is the flux inside the transformer, you have to use this formula. So the formula usually not given. So E is basically N1. So N1 flux W over square root 2. Okay. So this is the formula. And W, if you recall, W is equals to 2 pi F. Okay. So E1 is just equals to 2 pi over square root of 2 n flux. This one is flux maximum. Okay, the peak. If you have something like this, okay, this is the flux m, maximum flux, because this is a sinusoidal. So this is something like this. Okay. So this one become E1 is equals to 4.44 N1 flux maximum frequency. So this is how you calculate flux maximum or induced voltage at the transformer. Okay, make sure you memorize this formula. E1 and E2 also the same, but only change is the winding. Okay, and to flux maximum frequency. Frequency and flux maximum stay the same because flux maximum is in series. That's why it is the same. Okay, this is ideal transformer, and try to remember this. Okay. V1, E1, flux 1, flux 2, flux M, E2, I2. Okay, so make sure you know the notation. Let me move this. So make sure you know how to draw this. Okay. Do the winding here. Do the winding here. So the currents, this is I1, okay? This is V1, this is E1. So this one is E2, this one is V2, this is I2, okay? Make sure you know the notation. Okay, this one is the flux, okay? Okay, important thing is you need to know what is the turn ratio. So turn ratio is just basically alpha equals to, or for this case they use A. So just use A. A is equals to N1 divided by N2 and equals to, okay, E1 divided by E2. Okay. And for current, make sure you inverse it. I2 divided by I1. Okay. This is an important relationship. Make sure you know. Okay. This one is the same, but this one is flipped. Okay. Make sure you know the relationship. And then for the power, okay, remember back the complex power, EI, II star conjugate equals to S1. And S1 is equals to S2 for ideal transformer. And then E2, I conjugate 2. Make sure you remember this. Okay. So A, okay, turn ratio can tell many things. Okay. Okay, for A, so make sure you know if A is equals to 1 means that N1 is basically equals to N2, E1 is equals to E2, I1 equals to I2. So basically this is just an isolation transformer. Okay, basically it's just for safety. Isolation transformer. And if A is less than 1, it is step transformer. Step up transformer. Okay. So A is less than 1 is step up transformer, means that N2 is larger than N1, E2 is larger than E1, and I2 is smaller than I1. Okay, make sure you know this one is flip. I always flip. Okay, so if A is more than 1, means that it's a step down transformer. Means that E2 is less than E1, Okay, the voltage is stepped down, so you have a larger voltage at the primary side, and the secondary side has smaller voltage. Okay, N2 is also less than N1. Okay, number of turn and E is correspond to each other. It's not the same value, but it is correspond to each other. And of course, I2 is more than I1. Okay, when you step down the voltage, okay, the current increase because of the relationship here. Okay, so if you recall here, I equals to S equals E1 I1 equals to S equals to E2 I2. If you increase the voltage, okay, the power is okay. If you increase the because the E is kept constant, because the S is kept constant, if you increase the E, okay, you reduce the I to make sure that the S is kept constant. Okay, make sure you know that relationship. So this is for the relationship between the turn ratio and the type of transformer. Okay, for the transformer, you have to look at two things. Okay, usually we look at the voltage ratio, okay, the primary and secondary voltage, okay, this one, and as well as the power rating. Okay, for small transformer is usually given by watt real power only. But for large transformer, it's usually given in apparent power. Okay, but usually for our case, we use the kVA. Okay. Okay, so ideal transformer, for example, one, determine the turn ratio of 5 kVA, 2400 volt to 120 volt power transformer. Okay. So how to do this? Determine the turn ratio. So remember the formula? Okay, make sure you try also for the example, okay, just for practice. So A is equals to E1 divided by E2. Okay, because they give the voltage, so you just use this one. So A is equals to 2400 divided by 120. So you get 20, right? The turn ratio is 20. Okay, so this is how you calculate the turn ratio. So because A is larger than 1, it is a step-down transformer. Okay. Okay, next we move on to the second example. Okay, ideal transformer is actually quite easy. So it is direct to the point. So next is how to calculate this is the step up, because you can see here the voltage at the primary is lower than the secondary. So this is a step up ideal deliver 50 kilowatt resistive load. Calculate the turn ratio. Of course, A is just equals to VE1 480 divided by 2400. So use your calculator. So 0.2. So this is the turn ratio. Okay. How about the primary current? So remember, alpha. Oh, sorry. Usually I use alpha A is equals to, okay, I2 divided by I1. Okay. So how to calculate the primary current? Okay, this is the relationship. So you can see here, this is an ideal transformer, and the power is, so your power is 50 kilowatt. So you have V1 is equals to 480 volt. So I is equals to, okay, so this one should have our factor, I think. Oh, resistive load only. Okay, so this one PF power factor is just equals to 1 because it is resistive load. Okay, So PF is equals to 1. So remember, recall back, P is equals to VI, okay, PVI cos theta, okay, or cos theta is just equals to PF. So I is equals to P divided by V PF. So P is 50, okay, 50K divided by 480 divided by the power factor is 1. So you get you have the primary current is equals to 104.17. Okay. How about the secondary current? So for the secondary current, you have to use this formula. Okay. So I2 is basically equals to alpha or AI1. So A is 0.2 multiplied by 104.17. You get so you get 20.83 ampere. So this is how you calculate the parameter, okay, the current voltage of the ideal transformer. Okay, here is another example. Okay, so somebody can try. What is the first step? What is the primary and the secondary current? How to calculate this? Anybody want to try?
We need to find the turn ratio first.
Turn ratio, yes, correct. Okay, first thing you have to calculate is the turn ratio. So remember the E1 and E2. So E1 is 1100 divided by 400, you get okay, you get 2.75. Okay. So you have the A, and now you have to find the current. So you have the S is equals to 250 kVA. Okay, and you have N2 actually. The has turned on the secondary means that N2. Okay, 80 turn. So how to calculate the current? Okay, so they give, remember S is equals to VI. Okay, recall back, or S equals to EI. Okay, so because we want to find the primary one, so primary current is I1 is equals to S divided by E1. So S is 250 K divided by 1100. So 250000 divided by 1100.
227.273.
7. Only take 2 is enough. Okay. How about I2? How to get I2? Okay. Anybody want to try? How to get I2?
Can we use the turn ratio and I1?
Yeah, also can. So recall back, I2 is A, I1. Is that correct?
Yes,
Okay.
that's right.
So you can just use it. Either you want to calculate again using S, or you can use the turn ratio you already calculated. So 2.75, okay, 2 to 7.27, okay, 2 to 7.27. So the answer is okay, 625 ampere. Okay. So if you want to make sure this is correct or not, you can see here this is a step down. step-down transformer because the voltage at the primary is larger than secondary. So if you use step-down transformer, the I1 must be smaller than I2. So you can see here this is correct. Okay. So 227 and 625. How about the primary turn? Okay. What is the formula to find the primary turn? Okay, you already have the secondary turn, and what is the formula? So
N1 divided by N2, right?
Yeah, N1 divided by N2 for equals to alpha.
Yes.
N2 equals to A. Okay. So N1 is basically A and 2. So N1 is equals to A is 2.75, right? 2.75 multiplied by N1. What is N1? 80.
80. Yeah.
Correct, right? Secondary? Yes.
220 turns.
220. Yeah. 220 turn. Okay. So this is how you calculate it. And the maximum flux, okay, for this one, remember, recall back, E equals to E1 equals to N1, okay, flux maximum and frequency, and don't forget the 4.44. Okay, recall back the formula, this formula. Okay, this one. Okay, make sure you remember this. Where is it? This one. Okay, the maximum flux. So how to calculate this? So you just manipulate this formula. So flux, maximum flux is equals to E1 divided by N1 F 4.44. Okay. So E1 is 1100 divided by 4.44. Okay, and N1 is number of turn, 1 is 220, and frequency is okay, 50 hertz. Okay, you can see it. This one is the frequency. So flux maximum is equals to, use your calculator. So you get 0.0225. Okay, or also 22.5 milliweber. Okay, that is how you solve the ideal transformer problem. Okay, so this one should be in the theoretical part. If you look at the transformer, they have a nameplate. Okay, something like this. Okay, they will show a tap changer here, the voltage ratio, the power rating. So you can see here the 370,000 kilo VA kVA. So this is a very large transformer. Okay, this is a 60 hertz. Okay. So different, you have to use a different transformer if you use a different frequency. Okay. So, okay, this one is also an ideal transformer. Okay. This one is repeated again. Okay, no need to worry for this. Okay, transferring impedance. Okay, so we move on to the next part, which is impedance. So previously I only show you alpha. A is equals to N1 divided by N2, E1 divided by E2. Okay, E1 divided by E2 and I2 divided by I1. Okay. So this is for number of turn, voltage, and current. So impedance is much more a little bit different. Okay, if you can see here, okay, you have to put square root of Z1 divided by Z2. So you can see here this follow this one and this one. Okay, but you have to put a square root. Okay, so this is the relationship for the impedance. Okay, this is how it is derived. Okay, alpha V2 and I2. Good. So it becomes something like this. Okay, this is how the relationship is obtained. Okay. Yes, this one. So if you move again, so Z1 is actually alpha squared Z2. Okay. Okay, sometimes Z2 is called Z load. Okay. So be careful. I should understand Z load and Z2 is the same. Okay. So after this, we will learn about the equivalence circuit in ideal transformer. So you can see here, this is the actual real circuit. Okay. So let me draw this. Okay, usually transformer, you have a AC source, and then you have the transformer. Okay, because this is ideal, it is much easy, just directly here. Okay, and you have a transformer. Sometimes they have this. This is just a type of core, if not mistaken. This is just a type of core. So this one again, okay. And then you have a Z2 or Z load. Okay, either way is the same. So you have I1. So this is V1. This is E1. This is E2. This is V2. Okay, so this is I2. So when you want to calculate this, it is difficult because you have this thing. Okay, you have the transformer. Okay, so we want to eliminate this. Okay, you want to eliminate this because you want to easier calculation. You want to make it as easy as possible. So how to do this? So basically, when you want to eliminate this, you have to transfer the impedance Z2 or Z load here into the primary side. So if you look here, okay, so this is the point. Okay, you can see here this is V1, I1. Okay, okay, this is E2. Okay, so at this point, you want to eliminate it, but you have to transfer everything here. Okay, so how to transfer this? Okay, it becomes something like this. So remember this formula. Okay, so basically at Z1, okay, because you want to transfer Z2 to Z1, so Z1 is just basically A squared multiplied by Z2. Okay, that's it. And this one becomes I2, okay, yeah, A divided by I2. So I1, okay, A. Okay, so make sure you be careful because this is keep changing. Okay, and this one is E2 is equals to A E1. Okay, sorry, this one E1. This one is E2. Okay, make sure you know the relationship, how to transfer this one to primary side. So basically, this one is transfer impedance. If the question asks you to transfer the impedance, okay, you do this. So this one transfer impedance to primary side. Okay, this is transfer impedance to primary side. How about you transfer impedance to the secondary side? Okay, so if you have a something like that originally, so you have this one. So the secondary side you kept constant. This one is I2. This one is Z2. Okay. So if you want to transfer it to the secondary side, this one is E2. And all the primary side you have to transfer to the secondary side. So this one is the transfer to secondary side. Okay. So basically, this one is E2 to E1 divided by A. And the current is I1 multiplied by A. And then this one, so you have V1 divided by A. Okay. So this is how you transfer to the secondary side. So depending on the question, sometimes they ask you to transfer to primary, sometimes they ask you to transfer to secondary. But normally, they will ask you to go to the primary side. Always go to the primary side. Okay. Okay, this is I already explained before, just to eliminate the transformer. Okay. So this one, okay. So okay, this one is transferred to the secondary, right? Okay. Okay, this one's when the secondary is transferred to the primary side, when the primary source is transferred to the secondary side. So this one, I can write. Okay. So this one transfer to the primary side, the second one transfer to the secondary side. So make sure you have the skill to do both. Okay. So next we move on to the practical transformer. So we have a break. Okay. 10-minute break before we continue to the next part. In the meantime, take your attendance.